Good afternoon. My name is Gustavo Fonseca, and today we will be presenting Saving Lunar Trailblazer. This is our proposal for saving the Lunar Trailblazer mission, and it's part of our final project for the Astrodynamics ARO5090 course of Cal Poly Pomona. This is an overview of the outline of the slides that we are going to go through this presentation. You're going to basically see all of these ones, discussions in detail in the next slides. And well, the project is based on Lunar Trailblazer. Lunar Trailblazer was a small satellite made by NASA JPL and Caltech. The intention was to send Lunar Trailblazer to the moon to map the moon surface and to detect where the water was located in the moon surface. They actually wanted specifically to see the polar regions, since the polar regions are full of permanently shadow regions. That it's where they have the higher hypothesis where the water would be. And these places are key because that's how they're going to plan future landings missions. Unfortunately, by February 26, 25, Lunar Trailblazer lost communication and entered in an heliocentric orbit, basically missing all the planned trajectory of the mission and the correction maneuvers that they had to plan for the spacecraft.
This is an introduction to some of our analysis and tools used. We redesigned the Trailblazer's trajectory to meet the delta V distance constraints using MATLAB and SPICE for data extraction and simulation, while exploring options including direct transfers, Earth flybys, and asteroid-assisted paths. Next slide, please. Here are some of the assumptions we used in our calculations. For our assumptions during the calculations, we only worked with the Sun, Earth, and Moon as sources of gravity, assuming all maneuvers to be instantaneous delta Vs. Delta V constraints show the model is expected to be within operating safe range. We assume the model to be unaffected by radiation, pressure, drag, and thrust limitations. Next slide, please. We generated a pork chop plot to identify the best Earth transfer window, solve Lambert arcs for both legs, and use in-body integration to propagate the system and design a safe capture orbit. Next slide, please. We calculated the maximum safe arrival speed at the moon and confirmed the Earth flyby feasibility through turn angle checks. Next slide, please. We modeled the Earth flyby using hyperbolic equations, applied Lambert's method to link to the moon arrival, and used MATLAB ODE45 to solve the trajectory with in-body dynamics. Next slide, please. We used elliptical orbit equations and Lambert's method to determine Trailblazer's arrival conditions, then calculated the delta V for a stable capture orbit.
This is our final design and sun center trajectory of the Lunar Trailblazer. And from the image shown to the right side, we can see the propagated Lunar Trailblazer orbit that is moving faster than Earth. So it's gradually pulling away, confirms that the LTB is not bound to Earth and it's escaping. This helps us understand when and how to switch from this orbit to the moon Sun-Moon system, and sets the context for planning a Lambert arc to near-Earth orbit. Next slide. Earth center trajectory of the Lunar Trailblazer. This shows the image from 2025 to 2027. Next slide. And this shows the Earth center LTB trajectory with the 500 million kilometers constraint. This identifies the amount of time that we have to make the maneuver until we lose contact past the 550 million kilometer constraint. Next slide. And this is the pork chop plot to determine the optimal delta V for the LTB to Earth return transfer. And according to this, for the part the one the time with the most optimal delta V would be from June 30th with an arrival date of November 18th. Next slide. And this shows the picture of the LTB with to Earth transfer via the most optimal delta V Lambert arc in this heliocentric frame. Next slide.
This is a zoom view of the Lambert transfer. The Magenta arc connects the departure of the lunar trailblazer to arrival at Earth's position, which closely coincides with the propagated trajectory of the lunar trailblazer, validating the accuracy of the Lambert solution. Next slide, please. This figure shows how the lunar trailblazer uses an Earth flyby to change its trajectory. The Magenta arc shows the arrival from the sun-centered Lambert transfer. Following the flyby, the lunar trailblazer follows the Earth-to-Moon Lambert arc in a maneuver that saves delta V by utilizing Earth's gravity to redirect the trailblazer. Next slide, please. This plot is a zoom view of the flyby geometry near Earth, in which Magenta vector is the inbound lunar trailblazer trajectory, the black vector is the outbound Lambert arc towards the moon, and the green circle is the Earth's sphere of influence to help visualize the redirection and how close the flyby needs to be to achieve the necessary turn angle. Next slide, please. Next is the plot of the largest elliptical orbit that the lunar trailblazer can enter and still be gravitationally captured, which is at the parallel altitude of 100 kilometers. We can then compute the maximum arrival velocity that results in the capture. The arrival speed is then used to calculate the Lambert arc of the Earth, ensuring that the spacecraft is not too fast upon re-entry. Next slide. This figure illustrates the lunar trailblazer's initial capture into lunar orbit via a near-parabolic trajectory. As mentioned previously, the spacecraft achieves a parallel altitude of 100 kilometers, just meeting the mission's minimum constraint for a successful capture. Next slide, please. This plot shows the lunar trailblazer's moon-centered approach and orbit intersection. The dashed line is the incoming trajectory, the red point marks the parallel, and the cyan path represents the final 100-kilometer circular orbit. Lambert arcs and intermediate elliptical paths illustrate key maneuver segments. Next slide.
So as a summary here, you can see 5 of the main stages of the mission. First, we initially plotted all the positions of the celestial bodies around the sun in a sun center frame. This helped us to basically then later on decide the port chop plot that gave us the ideal time to do the maneuver, right, to change from the lunar trailblazer heliocentric orbit to the Earth orbit. And basically, once we pointed to the Earth and reached to the Earth, we used the lunar insertion orbit that we wanted to reach to do an inverse Lambert and then calculate how much the flyby will be required in the Earth to be done, right? Doing this approach, actually, we were able to reach moon orbit and to be captured by moon gravity and get 100 kilometers per year. Unfortunately, the problem with this approach will be that we are exceeding the amount of delta V that we are able to use, right? This is more than actually what the project mentioned, and it was the requirement. So it's part of the recommendations that we have for the project. So part of the recommendations would be to recalculate the Lambert transfer orbits and basically prioritizing lower delta V's, even if they result in a longer time of flight. Also, probably exploring multiple Earth flybys, maybe not one, maybe 2 or 3, right? That can stop the speed to the aircraft a little bit more to then reach the moon into a slower speed that will make an Apollon smaller, right? And definitely that gives us also more room to then spend more delta V in the corrections maneuvers that will be required to make the leap smaller into a circular orbit in the moon, and then to correct the orientation of that orbit. And at the end also, well, we can use the all these plots to see which asteroids are passing close to lunar trailblazer path, and maybe evaluate if those asteroids inserts could be used in a flyby. Here you can see the resources that we end up using for the project. And in this slide, you can find the link where you can find the MATLAB code to all these solutions. And that will be all our project. Thank you so much for your attention. And once again, thank you.